where I can see your faces and see everything on my screen that I need to. So you're just going to have to be more verbal. No more nodding, okay? So we said that we're trying to build a one-line accumulation function, and that's going to, the main structure is going to be the sum of accumulated bits from completed intervals plus a little bit more accumulation in the current interval, and all of those computed by rate times change in x, right? And so we figured out, I think we got to the point where we said that we know that in the completed intervals, what did we come up for in the jth interval? What was the x coordinate to get the rate for the jth interval? Do you remember that? What was the x coordinate to get the rate in the jth interval?
It was a plus the quantity of j minus 1 times delta x.
That's right. To get to the jth, the left side of the jth interval, you go across j minus 1 intervals, right? So you can start a plus, go across j minus 1 delta x's, and that gets you to the left side of the jth interval, okay? And so we said we're going to sum those up, starting from the first interval. And so this was something we hadn't done yet. This was to the number of intervals, right? Number of completed intervals. So that we have to figure what that out. So what is that? Because that changes with x. Every time x makes it through another completed interval, well, now there's one more completed interval. So this number of completed intervals is some expression of x, right? It's going to keep changing as x increases through the intervals. Okay, and then plus, we said, r of, so what is the x value of the left side of the current interval? We had a special name for that. What's the x value at the left side of the current interval?
Left of x.
Yep, that's this left x function. That's also something we're going to work on today. And then how much change do we have in the current interval? What is how much change? Do we have delta x?
Dx.
Right, and dx is that constant or variable?
Variable.
Right, that varies, right? So this is how far we've gone in the current interval, and so it's gonna start at 0, and then it's gonna be increase to as much as delta x, and then when it gets to delta x, well, then we hit the next interval. It's gonna start over, right? So this is our basic structure of the one-line accumulation function, and so all we really have left is so figure out exactly what left of x is and what the number of completed intervals is, and then we got it. Okay? So any questions on that recap? And so in essence, right, so this is starting to get a little complicated. We got lots of nuts and bolts here, some, lots of function notation, but again, this whole thing boils down to what? Summing up bits of change from completed intervals plus a little more change from the current interval. Right? And every one of those changes is computed how? How do we compute every little bit of accumulation? So at this point, you all should be jumping in to answer within a couple seconds. How do we compute a little amount of accumulation?
From constant rate of change.
What's that?
From constant rate
okay,
of change.
and how do we, and yes, use a constant rate of change, and how do we calculate it?
It's like the constant rate of change at the start of a very small interval of time.
So it's just the rate then? The amount of accumulation is just the rate?
Times the length of the interval.
M times dx, right? Over and over again. Rate times change in x, rate times change in x, rate times change in x, rate times change in x. Add them all up. Keep a running total, right? Keep a running total of how much accumulation of bits we have. So it all just comes down to this, adding up a bunch of these, right? A bunch of dy's. Okay, so let's try to, so now we're going to figure out what is the number of completed intervals, what is this function left x, and once we have those, then we're pretty much we pretty much have it. We pretty much have this one-line accumulation function, approximate accumulation function. We're going to take a look at, maybe, wow, a lot of, there we go. So let's look at this. I'm just going to do it manually here. So here I have, you can see up above, A is 2. Starting value of x is 2. So that would be back here. It's a star, so that's kind of like we're going to start accumulating from. My delta x is 1.4. And then this big X up here is the current value of x. Okay, and so then we're going to let x increase through those delta x intervals. And as we do that, you see the approximate rate function forming above. Do you see that? So it's blue in the current interval, and then it leaves behind the black steps in previous intervals. And so what are we after here? We're after, given a value of x, how many completed intervals, right? We said this is an important missing piece to our function. How many completed intervals? So let's just go right here. So here is A is 2. Delta x is 1.4, and we're at 8.6. Okay, so x is 8.6. And so I want you to tell me how many completed intervals for this value of x. How many completed intervals are there? And you can figure it out however you want. Any way you can figure it out, how many completed intervals do we have?
We have 4.
4. Is that Angel?
Yeah.
And Angel, how'd you get that?
I did it by counting the number of intervals that
Yeah.
were complete.
Just look and count them, right? There's 1, 2, 3, 4. Right? So for x equals 8.6, the number of completed intervals is 4. Everyone, does it make sense? And then we're this far, and what's this quantity right here? What's that?
dx.
That's dx, right? Changing in the current interval from 0 to delta x. Okay, and we got 4 completed intervals, and then the current interval is like the 5th interval. Okay. All right, so counting. Yeah, that's how we're going to get the number of completed intervals, by counting. Let's do another example. So now I'm going to change delta x to, say, how about 0.8. Okay, and then let's make x, say, here x is 7.2. How many completed intervals?
Six.
Is that Donna?
Yep.
How'd you get 6?
I added up all the black line segments.
Oh, you just counted? You counted them?
Yeah.
1, 2, 3, 4, 5, 6. Right, the black line segments represent complete intervals. 6. Okay. I think this makes sense, right? No, nothing scary or difficult about that. All right, so then what about if delta x was 0.42? Or how about 0.12? 19. There we go. And my current value of x is 12.2. So x is 12.2, and I want to know how many completed intervals. How many completed intervals do we have?
Too many for us to try and count.
Yes, right answer. Too many, right? We might be able to do it, but yuck, who wants to do that, right? So, but I still need to figure it out. How many completed intervals? All right, so I've got a equals 2. Right, and I've got x equals 12.2. And my delta x is 0.19. So everyone think for a minute, how can we get the number of completed intervals from the information, right? So certainly from these numbers that I have, that's all determinant of how many completed intervals. So there has to be some way to get it from these values.
Can we like subtract x and by a and then see how many times 0.19 can go into that number?
All right, cool, very good. So she wants to do let's start a new line up here. You want to do x, so 12.2 minus a is what you said.
Yeah.
So what would that number represent? 10.2. What would that number be?
Like the complete distance between those 2 points.
Yeah, that would be like our change so far in x, right? That'd be how much x has changed. And then if you want to get how many intervals are in there, what would you do?
You divide by 0.19.
0.19. What about the rest of you? Does this approach make sense?
Yeah, almost.
Yeah.
Almost.
Okay, so Richard, you're saying almost. What do you mean?
Because like the number of intervals, like that gives you the number of intervals in total, but not the number of completed intervals.
Okay.
So if we use like
No, hold on. Let's just look at it. So, tell me, how many completed intervals?
53.
53. So you didn't round up. Why didn't you round up? Because 53.7 or 53.6. Why didn't you round up?
Yeah.
So why not round up?
Because we currently have like 0.6, the length of 0.6 of an interval.
Uh-huh.
It's not a full interval, so
Okay.
it's, yeah.
Right. So even if this were 53.95, how many completed intervals?
53.
Still 53. So we got the general structure of this, but what we need then is just to what? Like just lop off the decimals. Would you agree with that, everybody? So it's like I'm going to get this decimal version, which is going to give me the completed intervals and something like the fraction. This is like the percent of the partial. Percent of a completed interval, that is the partial interval. You see that? So it's like we're 68% of the way through the current interval. Does that make sense? But we just want the 53. We just want to like make that go away. No matter what, we don't want to round. We just want to chop it off, and then the whole number will give us the completed intervals. So there's a mathematical kind of function or operation that does this. Does anyone know what that is?
The floor function.
Right. This is called the floor function. The floor function does exactly what we need. If you have a decimal version of a number that's not a whole number, it'll just takes off the decimal part. Okay? In GC, let's save this here. So I'm going to cut. In GC, you just type in floor, F-L-O-O-R, and you get these kind of square brackets with the floor on it, but not a ceiling. See that? And now if you put in that expression, lo and behold, what does it give us?
The completed intervals.
Yeah, it did exactly what we wanted. Just cut off the 0.684, right? So it just cut out the 0.684 and gave us the 53 by executing the floor function on that ratio. Okay, let's do one more example, and then we'll generalize the formula. So how about delta x of 0.07? And I ran out of intervals here, so, and let's make x 5.76. So I want you to figure out how many completed intervals, right? So just do the process one more time, like from scratch. A is 2, delta x is 0.07, x is 5.762. How many completed intervals? So how about Elizabeth? Are you catching on to this?
Yeah, so you would just like have to find the difference in like how much dx you have. So that would be like 5.76 minus 2. And then you would divide that by your delta x, which is 0.07, and then put that in like a floor function.
Exactly. Exactly. So let's do it. So 5.76. And then over 0.07. Huh. Now that is weird. Same number. It's my lucky day, I guess. So that I just made up these numbers out of the blue, and we got the same number of completed intervals for the two examples. But obviously, I'm more amused than you guys are. All right, so general then. So now a general formula. Number of completed intervals is? So
the floor function of x minus a divided by delta x.
Okay, so this is super good, right? So this was how many, given a value of x, it's how many completed intervals it is, and now that's going to help us with that sum, right? The sum of all the change from completed intervals. Now, given a value of x, we'll know how many terms in the sum there will be, right? Given a value of x, knowing a, knowing delta x. All right, so there's only one more piece of this puzzle, and that is what is left of x. What is left of x? So let's graph it here. Let's make it bigger again. So if this is the number of completed intervals, how would I write an expression okay, it's all gone. All right, so how would I write an expression? So number of completed intervals, is x minus a over delta x, the floor of that. So what is left of x? Now that we know how many completed intervals there are, 2x, how do I get the x value at the start of the current interval? Ashley, you want to give that a shot?
I guess if you did your number of current intervals times dx, or delta x.
Times delta x?
Yeah.
Okay.
Plus a.
So she wants a plus the width of each interval times the number of completed intervals, and that'll give you this x value. What about the rest of you? You agree with that?
Yeah.
Yeah. Exactly. So we have it. We have everything we need now for the one-line accumulation function. We know what left x is. We know what the number of completed intervals is. We know how to get to the left side of any completed interval. It's a plus what? J minus the jth interval. You know that, right? So if this is the jth interval, to get to that left side of the jth interval, we're going to go across j minus 1 intervals times delta x plus a. Left x will be all the completed intervals, right? All the completed intervals to the left side of the current interval. So we got everything. So let's put it all together. It's better than you think. Let's see. So here we go. So how many complete intervals to reach the current interval? How many completed intervals to reach the current interval? See all of them, and we found out what that was. So actually, we're just going to use this. What is this whole thing? We wrote it before. This is what? The starting value of the current interval, which we called what?
Left of x.
That's left of x, right? And we said that left of x is a plus the total number of completed intervals times delta x. That's left x. Accumulation due to completed intervals was this, right? So this was the rate at the start of the jth completed interval times delta x, and j is going to cycle, start at 1 and go 2, go 3, and then how many completed intervals do we have? Or I'm not there yet. Plus accumulation so far in the current interval, right? Which is r of left of x. So all we have left is this missing piece here. And what would dx be, right? We don't have dx in this. We want dx to be a function of x, right? So we want an expression of x there that gives us dx. So again, how many completed intervals? What did we find?
The floor function of x minus a over delta x.
Very good, right? That's how many completed intervals there are. You guys figured that out. And then how can we say what dx is in terms of x? So what is this variation in x in the current interval?
Is it x minus left x?
Okay, Donna's offering up x minus left x. What about the rest of you? What do you think of that?
That's good.
Yeah, good. So we got it. This is it. We got everything we need. We're gonna count completed intervals starting at 1. For each interval starting at 1 up to the number of completed intervals, we're gonna have a m change in x, right? And we're gonna add them all up. M change in x plus m change in x for the completed intervals. Plus the little more accumulation for the current interval. Oops. I had a pretty graphic. What happened to it? Let's see here. There we go. So this is our one line net accumulation, approximate net accumulation function. The one line, approximate net accumulation function. Do you remember what the difference between net accumulation and total accumulation was? We talked about that a couple classes ago. Anyone remember what that was? Why am I saying net accumulation? What does that mean?
It doesn't account for like what you started with.
Okay.
For A, I guess, or at A.
Right. So this would be all the accumulation. What? Starting from
Starting from A.
Starting from A. So it's how much change in the quantity from a given starting point of x. A. So you say A here and A here. Okay. If to be a total accumulation function, then we'd like have a lump sum of all the previous accumulation up to A, and we would just tack that on, right? We just as a lump sum. And then starting from A, we're doing this very mechanical process of interval by interval, cranking out bits of accumulation, adding them up, and keeping track of the running total, right? Keeping track of the running total of bits of accumulation. It's so good. You won't find this anywhere else. Dr. Thompson, Pat Thompson, if you guys know him, he just retired. Extraordinary math education professor. He created this here at ASU in the last 10 years, which I have working. So this is unloading sand on a scale. Okay, so this is for the context of unloading sand on a scale, and this is over here was the rate of change of weight as a function of time in 100 pounds per second, and so that looks like this. And so at some point in time, right, at some point in time, the sand was unloading out the back of the truck onto the scale, and there was a certain rate for every moment of time of the sand unloading, and so as time went by, there was all these correspondence points of time and rate, and so that's this graph is the is a certain perspective on that by correspondence points of time and rate. Okay, and why does this make sense for sand unloading out of a truck? Why does this rate function kind of make sense?
When you start pouring the sand, it comes slowly,
Mm-hmm.
but then as more sand comes, it like speeds up
Mm-hmm.
the pouring process, and then when you get to the last remnants of sand, it slows down again.
Exactly, right? You can imagine that, right? You can imagine a little bit comes trickling out at first, and then more and more and more, and then there's like the bulk of it in the middle. So that's a high rate of change of weight, and then as there's less left, it kind of comes up slowly and slowly, and then it just like trickles out, right? So this makes sense. And so this is view one. View one shows the generation of the exact rate function, R sub W. Okay, view two then. So here we have delta x. I can set delta x to 0.3, say. And view two shows this. It shows the approximate or the exact rate function statically, and then it shows the approximate rate function for a delta x of 0.3. Actually, 1.4. And it shows that kind of being generated as time goes by, right, point by point. So this is our approximate rate function. Okay, and so this function, so before we had a piecewise function, right? We just determined what the values were, and then we wrote it piecewise, right? It's approximate. Do you remember doing that? So first rate, second rate, third rate, first interval, second interval, third interval. Remember doing that?
Yep.
So now, with the tools we just developed for the approximate rate of change function, not only can you write the approximate rate of change function in one line, but now you can write this function in one line too. And I'm going to leave that to you. Okay? You have the tools that we just worked on today. So we built some tools that, you know, make it very easy, if you can conceive it, to write this approximate rate function, the blue one, as a one-line function. And actually, the function itself is very simplistic. Now, I'm not saying it's simple, like you should be able to, you know, you may have to think about it. It may be a little bit of a challenge to come up with, but the result is a very simplistic function. It's not very complicated. Okay. Okay. So that's view two. View two is the approximate rate function emerging. Okay, view three then is the approximate rate function along with the approximate accumulation function on in the right graph, emerging together. What kind of function is this? The approximate rate function? What do we call that?
The piecewise function.
Piecewise, yep, piecewise, and also piecewise.
The piecewise linear.
Right. Each piece is a line, right? Because it's based on the constant rates of change we have, right? So in each interval, based on a constant rate, so it's going to go up linearly, right? So that is view three. And so now we can think about so what about this approximate rate function? Good approximation or not so good?
Not so good.
Why not so good, Richard?
Those are pretty big intervals that we're basing it off of.
Big intervals, which means what about what happens in those big intervals that makes it not a very good approximation. So,
I just remember that like the more intervals you have, the better the
okay,
approximation.
that's true, but we should know why. So somebody else, do we know, looking at this approximate rate function, why do we conclude that it's a bad approximation? What is it about the big intervals that makes it very crude?
Because there can be big like changes in rates over our time and interval, like it's not constant during that time.
Right. So like this rate in the second interval, how does it compare to the actual rate in that interval? Pretty close? Is it matching?
Smaller.
Way smaller, right? It's pretty close just for a little bit at the beginning, right? But as soon as x, now we're starting to deviate greatly, right? And it's a huge deviation from actual rate to the approximate rate, especially in the second half of the interval, right? So is this approximate rate function, is it too big or too small? Are the values of the accumulation underestimates or overestimates?
I think it depends on which side of the graph you're on.
Okay.
On the left side, it's underestimates, but then on the right side, it's overestimates.
So around 1 is the high point. So you're saying it's an underestimate here. But then when we get to 1, are the values of A over here for x greater than 1, are those overestimates?
Yes.
What about the rest of you? Agree with that?
Yeah.
So remember, this is an accumulation function. What does that mean that it's an accumulation function? It's a running total, right? It's accumulating everything so far.
I think it'd be an underestimate the whole time.
All right, Sarah, why?
Just because like you just said, it's a total accumulation.
Right.
So our underestimates, like our bad approximations for like the first half of the graph, will still like, it won't be enough to get to the exact accumulation graph. So the rest of the graph, the red graph, like won't cover that change to get to the exact, or to even get over the exact.
Okay, the rest of you hear what she's saying? Understand that?
Yes.
So not only are we accumulating weight with this approximate rate function, but we're accumulating error, right? We have a lot of error from this first that we've accumulated. And now we're going to keep adding on to the error. And then keep adding on to the error. So that by the time we get to 1, it's a really bad approximation because it has all the contributions of underestimate the whole way. So now that the rate is too high for one interval, is this going to be an overestimate now? Oops, sorry. So let's say right here. So in this interval, the rate is too high. So is this accumulation going to be underestimate or overestimate? So Sarah says still underestimate. What about the rest of you? What do you think? Overestimate or underestimate at this point?
I think it's still an underestimate.
Right, because just this little bit of this approximate rate being too high for a part of an interval is not nearly enough to catch up for all the accumulated the accumulated amount too low that we got. And so maybe by the very end, it would like catch back up and for a moment be right again. But it's gonna be an underestimate, a growing underestimate, and then an underestimate that's kind of recovering here. Does that make sense? So how do we make a better approximation function? Oh, so yes. Yeah. How do we make the accumulation function better? If it's too low, how do we make it more accurate? Not just higher, but more accurate.
Make your delta x smaller.
Right, and here's the beauty of this. The beauty of this file is that all I have to do is change the delta x slider. It'll change my interval width, it'll change my approximate rate function, and it'll change the approximate accumulation function. So when I make delta x smaller, what are you expecting this approximate accumulation function to do?
To be closer to like the actual exact accumulation graph.
Yeah, right. So watch it. Keep your eye on the accumulation function. I'm going to just choose it. What do you see that it did? Did it move up or down?
Up.
You should have seen it moved up.
It kind of like smoothed out too.
Is it smoothed out? So I'm going to a delta x of 0.16. So here are my 0.16 intervals with a new approximate rate function, the blue. And now here's my new a function. Is it smoothed out? Is it a smooth curve?
Not like perfect, but more than it was before.
Okay, so yeah, so like, right, it looks more curved, but is it any less of a piecewise linear function?
No.
Yeah, so in every interval it's still linear, perfectly linear. And we saw that it moved up, and that's because we predicted that this was going to be, we gained a lot of underestimate in the first half, and then we tried to recover and catch back up, but it's still going to be an underestimate in the second half. Okay, so I'm going to make delta x smaller again, and then you're going to tell me if you see it move or not. Okay, ready? Did it move?
Yeah.
If it moved, that means we still have a approximation that's not exact, right? So as we make these delta x intervals smaller and smaller, we're moving closer and closer to the exact accumulation function for the exact rate function. So I'm going to do it again. Watch it. Tell me if you see it move. Ready? 1, 2, 3. Did it move?
Yeah.
It moved. Okay. So we're still in approximate mode, right? As long as we can make the delta x interval smaller and it gets like better, we're still in approximate mode. But look at this, it's 0.0144, and I took away the exact, this is actually the approximate rate function now. So if I zoom in, do you see that's still a bunch of really narrow steps? It's still an approximate accumulation function, or sorry, approximate rate, and this is still approximate accumulation. All right, so I'm going to move closer again. So I'm going to move delta x, watch A, ready? Did it move? It kind of had to regraph, right? It had to regraph itself. But so there comes a point with these delta x's where making delta x any smaller doesn't make a difference between these a functions, right? The delta x is so small that if you make it even smaller, you don't really see any, there's really no, the difference between accumulation functions is negligible. And so that's when we say we have the exact accumulation function. So exact accumulation occurs when? Making delta x any smaller means no practical difference between a functions, the previous one and the new one. So it's the idea of essentially equal, essentially equal. We could keep making delta x smaller, but it's not really changing anything for practical purposes. So we call that essentially equal. And that's our conception of limit. So small that making it any smaller doesn't change the ballgame at all. So that's view 4. So I'm going to make delta x bigger again. And view 4 is showing the exact accumulation function. But the reason that exists is by making the delta x interval smaller and smaller until the a function doesn't change anymore, and that's when you know that you have this exact accumulation function, the black one. So again, making the interval smaller and smaller until here I'm at 0.0005 for delta x. So small that it can't even graph the approximate accumulation function anymore. Okay, any questions on? So this is we were kind of advancing the conversation, but I was also showing you this next project, right? That this is what you're creating. You're creating this file that has 4 views. The exact rate, along with the emerging exact or approximate rate, and then the approximate accumulation function for that delta x and for that approximate rate, and then view 4 shows the exact accumulation function, which matches up with the red exact rate function. So do I have the version for someone? No, I guess I don't. I thought there it is. So you don't have to have that there. I just want to talk about this. So that's the approximate accumulation function, right? That we came up with. And so the black, so we call the exact accumulation function will be a sub w. So the exact functions have the w subscript. So r sub w is the exact rate of change of weight, and then a sub w is the exact net accumulation of weight. And then the ones that don't have subscripts are the approximate. So just little r and little a are our approximate rate and accumulation functions. So how do we think of this? We think of this as this function, what? With a very small delta x. Small enough so there's no difference in approximations anymore. Nope, it's just small. And then when we reach that, we have a shorter way of writing this, right? We have a more compact way of writing this function when we reach that small enough delta x. And who knows what that is? You all know what it is, but did you know that this is what it is? That's the question. So what are we doing? We're summing up these bits of change, accumulating bits of change as rate times change in x, rate times change in x, right? And so when delta x gets small enough, we have like a gazillion of these, right? We have a gazillion of the m dx's that we're adding up and accumulating as we go. So does anyone connect with what the compact version of that is?
Integral.
That's what integral is. That's what integral is. Integral means the same thing as this with a very small delta x. So what are we going to have? We're going to have m times change in x here. So, but what is our rate? Well, instead of the rate being these independent rates, it's like every rate, right? Because if the interval's small enough, you just think about taking every single rate along the way. So that's what r sub w. But we're not accumulating rates. What are we accumulating? We're accumulating bits of accumulation, which we calculate by How do we calculate a bit of accumulation? Again.
Rate of change by change in x.
Right.
Over
Times.
small intervals.
Yeah, times. And so we're going to call that d. Think about that. Our little a little variable change in each interval, right? In the current interval. The amount of change in the current interval. Okay, and then we're going to start accumulating at A, and this thing is a function of how far left we've accumulated to. So right now, so it's like this right here. It's a 2.35. So the x is here. So we're going to accumulate starting from A to x of the rate times change in x. But I'm using t's here, and you need to use a different symbol. So what is this? This is every x from every value of x from A to x. Why can't I put x in there? Why do I need a new symbol to represent every value of x from starting from A up to the current value of x? Why do I need a new symbol? Anybody know?
Is it because you already used x for your bounds?
Okay, and so what would happen if I also used x there? So say, let's move back a little bit here. Doesn't matter. 1.8. All right, so here's x equals 1.8. What if I wrote A to x RW of x dx, and then I thought about A sub W of 1.8? What would happen? Do you see what would happen? If I do, so now it'd be A to 1.8 of R sub W of what?
Of 1.8.
Of 1.8, right? So it'd be like this is if we did RWX dx. It'd be A to 1.8 RW of 1.8 dx. Is it right? Will that give us the net accumulation according to this rate function? Here's this is the point 1.8, RW of 1.8. That point right there. So will this give us the net accumulation of our weight quantity according to this red rate graph? That's what we want, right? We want the net accumulation of weight according to this rate profile up to 1.8. Will this do it?
No.
What will it do?
Wouldn't it use that rate at 1.8 for every value since A?
Yeah, that's a constant. Do you see this? That's a constant rate. And so it's going to, starting at A, say A is 0, it's going to, this expression that I put a box around is going to accumulate according to this graph here, R sub W of 1.8. Will that give us the right accumulation of weight? No, it'll be way too low, right? It'll just be this constant. It'll just assume a constant rate for all x values from 0 to 1.8. That's why for any value of x that we choose, for any value of x, say 1.8, we need a new symbol that represents x changing from A to 1.8, so we get the rate profile, right? We get every rate as a function up to the current value of x. So we use another variable to do that. If you you use x, then any given accumulation will be based on a constant rate, the constant rate at the current value of x for the whole for the whole, all the way starting from A. Okay, so we made it. You know how fast a quantity is changing at every moment? We wanted to know how much of it you have at every moment. So given the exact rate function, this function right here gives us how much we have at every moment x based on the changing rate from the starting value up to x. By what? Summing up little bits of accumulated weight calculated by rate times change in x. This does not accumulate rates. So this is where we really got to emphasize. We're not accumulating the rate. That doesn't, if you think about it, that doesn't make sense. It's not accumulating rate. It's accumulating weight. It's accumulating bits of weight by multiplying the rate times little change in x and adding all those up. All right, doesn't make sense. Does this whole thing about the t's versus x's make sense? Why we need t, and we can't use the same, basically the point is you can't use the same symbol as the independent variable there also in there. That won't work because you'll always be accumulating at that constant rate for the whole way from a to your current value. So t represents every value of x from a to x for every given x.
Is t a variable then?
Yes, t, right. Because yeah, t is going to...
And is x a parameter?
No. X is the independent variable of the function.
All right.
So x is how far we're accumulating to. But for every amount of accumulation, we need to accumulate all the way from a to that value. So we need t to change from a to x. But then this function is a function of x, is a function of... so that we can know how much accumulation we have here at 1.98 and here at 2.08 and at 2.27. But for any one of those values, you have to do all the math from 0 up to that. You have to do all that accumulating from 0 up to that, whatever that value is, by summing up these bits at the varying rate. So to get the varying rate, we need a new symbol that represents every x value from a to the current value of x. So x is like the left side, the right side. So x is the current value, right? So so it's the x value of this point and of this point. Or you can see it by this vertical line. That's what x is. In order to get any of those accumulations at any value of x, we have to let x go from a to x, and so we use t to do that. And we accumulate all the way from a to the current value of x to get that current amount of accumulation. Okay, so there's this really integral, this integral function is this. It is this thing that we've worked on the last couple of class periods, just with a small delta x. Small enough so that we can't tell the difference between approximations. So once we get to the point where can't tell the difference between approximations, this function can also be written this way. Integral. So let's do it. I got a summary slide here. So here's kind of where this is approximate and exact accumulation. So this should look familiar from what we're doing here. These are the four functions. Which function comes first in this process? Which function comes first?
The exact rate of change function.
Exact rate of change. What's the next one we build from that?
The approximate rate of change.
Approximate rate of change. And from the approximate rate of change we can build?
An approximate accumulation.
The approximate accumulation. And then from approximate accumulation functions with smaller and smaller delta x, we get the exact accumulation function. So here's our approximate net accumulation function. That's the one we built today. So what's the exact net accumulation function? That is the integral, right? And we said this is essentially the same as this with a really small delta x, right? This is the same, exact same thing as this with a really small delta x. Okay, so if the scale already had p 100 pounds of sand on it, the function, so this is the net accumulation of the function f. So the function f, or in this case, it was called w before, but I switched it to f. F then is the total accumulation, right? Difference between net accumulation and total accumulation. So how would we write the function f? If it already had at x equals a, it already had p 100 pounds of sand on it, then what would the function f, or the total accumulation, be? Yasra, can you tell me what that would be?
It would be the same thing we have to just add the extra p at the end.
Yeah, exactly. Well, can I add at the beginning? Is that okay?
Yeah.
Yeah. So this is the total accumulation, f, right? And this we would have called that weight, and everything. All the previous slides and animations would have been w. The w function is all the total weight from before a, and then plus the accumulated weight as x changes, right? As time goes by. This gives us the accumulated running total of weight since a, since time a. Okay, so in your math career, is this the way you thought of integral in the past?
Definitely not.
Okay, we got one no. What about the rest of you?
Yeah, definitely not.
Okay. So what was your conception of integral? So like when you think of integral, what came to mind? What comes to mind from before this?
It's the area under a curve.
Right, area under the curve. Okay, so do you see how this has like it's much more relevant, this kind of approach to it? Because this net accumulation can be the accumulation of any quantity. Weight. We can accumulate changes in speed to get speed. We can accumulate changes in distance. We can accumulate mass. We can accumulate changes in temperature to get a temperature function. So rather than just like kind of reducing an integral to just area under the curve, we build an approximate accumulation. Think of it as approximate accumulation, and it applies to any real-world quantity that's changing, right? That's changing with respect to some independent variable. Does it make sense? Okay, let's skip this slide, and let's do this slide. So why don't we do breakout groups, because I think I'm talking a lot, and see if you can get through this in 10 minutes, okay? So let's make some breakout groups. Jeez. You can't see this when you're in the breakout groups. So I would need to provide this ahead of time. So that's not gonna work. So let's just talk through it together, but let's make it a discussion rather than just me doing the talking. So a tub has a clogged drain that still lets some water through. At t equals 0 minutes, the faucet is turned on. The following graph shows the rate of change of volume of water in the tub in gallons per minute as a function of time in minutes. So this is the rate of change. Gallons per minute. And then this is minutes. So it's the rate of change of volume in the tub. It's changing. So the amount of water, the rate at which water is going into or leaving the tub, that rate is changing according to this. All right, so what do you guys think? The first question is, at what time does the tub have the most water in it?
Would be the very, very beginning.
The very beginning. Because this is the amount of water decreasing. Is that right?
Yeah.
What is this again? What does a point in this mean? So let's pick a point here, 1.5. And so this is volume, so we'll call this the RV function. So this is 1.5 and RV of 1.5, which is about what? $1.2? 1.3? We'll say 1.3 gallons per minute. What does that point mean? So what does that point mean for our tub situation?
It means like the rate of change of the volume of the water is approximately 1.3 gallons per minute at 1.5 minutes.
Well said. Well said. That was excellent. And so what's happening in the tub right now at 1.3, 1.5 minutes? What's happening in the tub?
I think it's still accumulating water.
Because?
Because the rate of change is positive.
We've got a positive rate of change. So is there water entering the tub or leaving the tub?
Entering.
She wants entering. What about the rest of you?
Yeah.
Ashley, what do you think?
Yeah, I think because it's in the first quadrant, the rate of change is, whenever it's there, is always going to be positive, so you're going to be like gaining.
Okay, so at what time does the tub have the most water in it?
So like wherever the x-intercept is.
Okay, why the x-intercept, Ashley?
Because that whole time before it was gaining more water,
Okay.
and then afterwards the rate of change becomes negative, so it's going to start losing water.
Okay. Angel, you agree with that?
Yeah, makes sense.
Yep, okay. So let's just kind of, before we go any further, let's think about how this could be the case, right? So let's just think it practically with the tub and the water. So we've got water's entering in, but at a slower and slower rate. And then at this point, then what happens to the water in the tub?
It starts leaving.
Yeah, now the total water in the tub is decreasing and at a higher and higher decreasing rate. So how could that be possible? Right? So the waters were filling up at slower and slower, filling up slower and slower. And now the water level starts to go down and then faster and faster going down. So let's just, I think it helps to say, talk about the tub and the water like you would, talking to your family members, standing in the bathroom. Why is this happening? Why does this graph make sense? Or how could it make sense? How could we make sense of this graph practically as we're sitting there staring at the bathtub?
Selling my bath water
What's that?
by skipping it out.
Okay, scooping it out. So let's go back to this scenario. It says a tub that has a clogged drain still lets some water through. And then t equals 0, the faucet is turned on. So what's happening? So it's turned on, so we're adding water, so that makes sense that we're adding water, but then the amount that's added to the tub is going, per minute is going down.
Is it like the tub is slowly getting unclogged?
Right, so if the clog starts loosening, it's loosening gradually, then what would happen? The amount that's going down the drain
Would slowly increase?
it would increase, like the rate at which so we could turn the faucet on and it's just pouring water in at a constant rate, but then the clog is like coming loose to the point where at this point, so what do we have? What's going on? Zero rate of change, meaning the amount of water going in is the same as the amount of water being drained, right? And now the drain is continually loosening and it's we're losing more water than that's what's going in. Okay, at what time does the tub have the least water in it? So what did we do? We added water this whole time. And now what's happening here?
We're taking it away.
Taking it away. So when is there the least amount of water?
I would say at t equals 0.
Why?
Because the period where we're gaining water is more than the period where we're losing water.
Mm-hmm.
So if we want to look at like the least amount of water, it would be at the beginning.
Mm-hmm. Yeah, we've lost some water here, but not as much as was gained. So that means there was less water in the beginning. Everyone good with that? Okay, so here's that function. And the tub started with 2.5 gallons in it. I want to write the function AV that gives the accumulated changes in volume, t minutes after the faucet was turned on. So I want to write A sub V of t. Again, this gives the accumulated changes in volume at t minutes since after the faucet was turned on. How do I write that function?
It's the integral from 0 to t of r sub v of just choose u, I guess, du.
Richard has offered this up. What do the rest of you think? Elizabeth, what do you think of that?
I think the integral is good, but if are we doing just like accumulated changes or like the total accumulation?
That's the right question, right? So are we asking for the total amount of gallons in the tub, or how much additional gallons since the faucet was turned on? What is it asking for?
It asks for accumulation, so then I think this is good if it's accumulation.
Well, both of the things you offered up are both accumulation. It's just as a matter of
the net accumulation,
right?
I
Net
guess.
accumulation, right. Exactly. So we want just the net accumulation. So we don't want that 2.5 because this is how much water has been added since time 0, and that's what this means. And good. So now t is our independent variable, but we need a different symbol to represent values of t starting at 0, ending at whatever t is. All right, what about v? So v of t. So now the volume in the tub t minutes after the faucet was turned on. Elizabeth, what's that going to be?
So then we would do like 2.5 plus the interval of like the a of t function.
Yeah. So because we did we already did the heavy lifting, we paid our dues to write this function, right? The sum r x plus r of left. We already paid our, we paid our entry fee by doing the hard work to come up with that. And we said that for very small changes in x, this is equivalent to integral. Well, now if we want to write exact net or total accumulation, we can just write integral, right? Because we know when we see an integral, so now for the rest of your math career, when you see an integral, you think of this, right? You think of, oh, we're summing up all the accumulation from completed intervals plus a little more from the current interval. but just with a really small delta x. That's what this means. And then to get a total accumulation, we just add in what we got at the beginning. It's so good. It's so much better than you think, right? We've just brought so much meaning to half of calculus, right? Integral, right? So we spent the last 2 weeks working on this approximate accumulation function, which we now see as integral when changes are, the intervals are very small. And so that it just brings this enormous amount of meaning to integral functions now because of all that work we did. Okay, so when did I have the sand unloading? When did I have that due? Did I have that due Tuesday?
I think it's Thursday.
Thursday. That's what I want. All right. So I want it to be due a week from today. So you definitely want to do as much as you can before Tuesday. Okay. You're not going to be able to sit down in 2 nights and finish that thing. So start working on it over the weekend. You can use the video from today's class where I demonstrated it. But this is now we're running with the big dogs now. This is complicated, hard stuff. But the payoff is that you get a really, really cool, good animation that will be very useful, right? So this is a super useful animation for understanding this, right? But the beauty of creating it is that you have to really know the math behind it to be able to create it. So as you in GC, as you need different things, like we talked about the floor functions today. If you want to do integral, it's Control-Shift-I. There may be some other commands like that. You can just email me. Oh, summation. Summation is, I think it's Control-Shift-S. Make sure. No, that was create a copy or save it or something. Maybe it's just Control-S. Okay, Control-Shift-S. Yeah, Control-Shift-S. So Control-Shift-S, Control-Shift-I is integral. Control-Shift-S is summation. If there's other things, keystrokes that you need for certain math functions, we talked about floors, just type in floor. I think that's everything you'll need, but if you come across something you're like, oh, I don't know how to do this in GC, just send me an email, or you can look in the help in the math menu, but feel free to send me an email and be like, what's the keystrokes for getting an integral or getting, etc. So don't, if there's something GC related that you don't know, just ask. Don't let that slow your progress down. Okay, any questions?
What does the equation slider do again?
You don't have to do that. That just makes that equation appear this. It just made this appear. So you don't need to have that. You don't need to have that. You need to have, and you don't need to have current either. Just view. So here's the function, but if you change this function, it should work for the new function if you change it. So that'll be in the video. And then you just need view and delta x. And as delta x changes, everything changes with it, right? So it's all based on delta x. So for PC users, you don't have a delta symbol for, so I've made this a parameter, 2-character parameter. For Mac, it's option J. Yep, so I did, backslash option J X backslash, and that made this. So you can type out delta X if you want. You don't want to do DX, but you could, yeah. So in PC, you can just come up with something, whatever is gonna work. Oh, one big last thing, and I'll let you go. In this, when you're writing this, okay, if you find yourself writing a formula over and over and over again in different math lines, what should you do?
Function notation.
Yeah, define a function for that, and then rather than repeating that formula over and over and over again, you can use function notation for the function that you defined. So please do that. If you're working on this and suddenly you notice, oh, I used the same expression here and here and here and here and all these different lines, define it as a function and then use function notation instead. Okay? That's super important. And I'll be on the lookout for that in your files. Okay? It's super helpful for just readability and conciseness, and then it just helps you. You know, it just makes it simpler for you to reread it and figure out what's going on. So as you're creating it. Okay, I'll let you go. So email me any questions you have, but that'll be due next Thursday.